Oh, good afternoon, everybody. It's great to see you all. First time ever, I'm going to lecture in a bar, sober. So, cheers to you all. The title of my lecture today is Coincidence is Logical. And I borrowed that title from um, Johan Cruyff. And I think that he was quite right when he said this. And during this presentation, I'd like to show you that he was absolutely right. Um, I'm going to present you in about 20 minutes time a short story about chance, and hopefully it will change your point of view, the way you look at the world, um, because I think as a teacher that is the highest goal one can achieve. Um, my name is Manfred Grotenhuis. I am a statistician at the Faculty of Social Sciences here at Radboud University. And well, here's a picture of good old T-Rex. At the moment, this famous meteorite hit the world. To T-Rex, it came as a complete surprise, of course. But for statisticians like me, well, we think he had it coming. And I will show you that these rare events like a meteorite that comes falling out of the sky, which is a very rare event. Well, it happens quite often. That's the strange thing I like to prove to you um, this afternoon. Well, when we talk about chance, then um, it's good to go back to the original meaning, which has something to do with falling, and you can find it also in the Dutch word for chance, which is toeval, and that means something that falls upon you, like in the case of the dinosaurs, or something that falls towards you. Other words for chance are probability and luck. And I have the feeling that nowadays these words are often used in a positive way, like winning a lottery or bumping into someone you haven't seen for a very long time, and you before you bumped into him, you thought of him. That is, related to rather positive events. When we talk about negative events like missing a train connection, we have the tendency to talk about bad luck, which is a very fine expression for something that is an event that it's not very positive or um, very pleasant. And the Dutch word, of course, for bad luck is pech. Well, in statistics, chance or probability is related to the occurrence of events. And preferably, we talk about rare events, meaning events that do not occur very, very often. And statisticians, they mostly are after the probability of such events. Well, when we talk about probabilities and rare events, we have to keep in mind that probabilities or chances, which are often are denoted with the letter P, which stands for probability, they are always somewhere between 0 and 1, or between 0 and 100%, if you prefer percentages over proportions. And I think in daily life we talk about chances in percentages. Well, rare events have a very small probability. Um, you can say it just doesn't happen very often, like 1 in 1,000 times. And today, to give you a first example of this whole notion that rare events often quite occur quite often, I have this example about scratching your car, and we know from insurance companies that the chances to have your car scratched during a single ride is about 1%, or the probability of 0.01. Oh, by the way, the picture here is a Ferrari Spider, which the photo was taken a couple of days ago in the city of Arnhem. It is a car crash. No one got injured actually, but it was someone who rented this car just before his wedding day, and the car has about 600 horsepower, and he unleashed it on a very wet surface. It rained, and the car got well, completely wrecked. Talking about coincidence. This probability to have a first scratch on your new car, like I said, is about 1%, or 0.01 if you want it in proportions. Well, it simply means that, you know, on average, 1 out of 100 new cars will have a scratch after their first ride. Okay, so we have 100 cars, we take them out for a ride, and after this ride, on average, one of these cars must have a scratch. But the question is, what happens if we take these cars out for many rides? Well, for instance, take someone who commutes to work in a car, and well, that must be 2 rides a day, right? 5 days a week. So that would mean that we have 10 rides in a week. So the question is, what are the chances to have the car scratched within a year? And well, to find the probability to have your car scratched within a year, we must recall that the chances to get a scratch on your new car during one single ride is about 1%. Now, after 2 rides, you may think that you can add those 2 probabilities. So we just add 0.01 to 0.01 to get 0.02. But that would be something that isn't right, because after 200 days, the chances would be 200%. If you still add all these probabilities, then you get chances that are way beyond 100%. And like I said in the beginning, probabilities never exceed 100%. So adding all these probabilities is a no-go. Well, what we need to calculate the correct chance of getting your car scratched, we need the chance of survival after 1 ride. And that is, we take just the probability to have your car scratched, and the total probability is 1. So if we take 1 minus 0.01, we get a survival rate. And that simply means that after 1 ride, the chances that your car is still unscratched, I almost said that the car is in one piece, but that's something else. I mean, the car is without a scratch after 1 ride is 99%. So after 2 rides, the chances to have this unscratched car is 0.99 times 0.99, which is 0.98. So after a week, we have 10 rides. Remember that we have this guy who commutes to work every day, so 5 days a week, twice each day. So if we want to calculate what the chances are to have an unscratched new car after a week, we have to take this initial survival rate of 0.99 times 0.99, 0.99, and so forth, until we have done this 10 times. If we do this, we get a survival rate of 90.4%. So the chances to have your car unscratched in a week, meaning after 10 rides, is 90.4%. So the chances to have a car with a scratch is 100 minus 90.4 is 90.9.6% chance to have your car scratched, which is still not much. Now, to multiply all these survival rates with each other, well, it doesn't look very elegant, right? So the solution to this multiplying is that we take the initial survival rate and we raise it to the power of 10, which is called exponentiation. So if we take this initial survival rate of 0.99 and we raise it to the power of 10, we get this 0.904, which is the survival rate after 1 week of driving in your car. Well, here's a little picture that shows how this exponentiation works. We take, say, the number 3, which is our base number, and we raise it to the power of 5, which means that we take 3 times 3 times 3 times 3 times 3. Okay, so now we know how to calculate the survival rate by exponentiation. We go back to the very start and we calculate some survival rates. And we start with just one ride. If we take one ride, then the chances to have your car unscratched is 1 minus the initial probability to have your car scratched, which is 0.01. So that amounts to 0.99, or in other words, the chances to have your car unscratched after one single ride is about 99%. That's a high percentage, so most probably your car will still be unscratched. Well, after 10 rides, which is about a week time, remember that we have a person who commutes to work 2 rides a day during 5 days, so that is about 10 rides. The chances to have your car unscratched is 1 minus 0.01 to the power of 10, which is 0.904, which is about 90%. So to have your car unscratched after a week is about 90%. Well, that's still quite high. But now we come to the final question. If we take 400 rides, which is about equal to driving to your work and back during a year, what are the chances to have your car unscratched? Well, we take again 1 minus 0.1 and we do that, we raise that to the power of 400. And as a result, we get a very, very low number. We get 0.018. So the chances to have your car unscratched is about 1.8%. Well, that means, of course, that if we like to find the chance of having a car with a scratch after 400 rides, we just take 1 minus 0.018, and that amounts to about 98%. So the chances to have your car scratched after 400 rides is about 98%, and that's a lot. And that is the explanation for the fact that almost every car has a scratch. Well, to compute the survival rate after 400 rides, I just, as a summary, I give you the formula again. Here we have the number 1, which is included in the formula just to flip the chances from getting your car unscratched to the chances of getting your car scratched. The other one here is to calculate the survival rate instead of the initial chance to have your car scratched. And here we have the initial probability to have the car scratched, which is 1%, and we have here this 400. We raise it to the power of 400 because we have 400 rides. Well, you may multiply it by 100 to get the percentages. Well, knowing this, we can come up with a formula which is, in my opinion, is even more important than this famous equation by Einstein, in which he equates energy and mass. This formula over here, where we have just, which is rather elegant, we have 2 times in number 1, and we have this P, which stands for initial probability that something occurs, and we have T over here, which stands for the number of trials or time, if you like. Um, this formula indicates that if we have a very rare occasion, so we have a p-value that is very, very low, but if we raise it to a very high number, which means that we take a lot of time, then the chances that this very strange event, very rare event will take place is about close to 100%. So that's very interesting. Very rare events sooner or later will appear, will actually become reality. That is what this formula is all about. Well, to give you a visual notion of what is going on, I just took this very important formula, and on the x-axis I just plotted the number of rides, and you see here this red line over here shows the probability to have your car scratched after that many rides. And what is interesting is that the chances to have your car scratched rises quite quickly. If we look at 100 rides, we have about 63% chance that we have our car scratched. And after 200 rides, we have about 86% chances that we have our car scratched. So after 200 rides, the chances are quite high that we have our car scratched. And you see that when we take it beyond 200 rides, the probability curve tends to flatten off because it cannot exceed 100. Well, this is a typical curve that you get when you use that particular formula. Okay, to give you a proof of this strange notion that very rare events have the tendency to occur quite often, I held a little survey among you in this bar, and I asked all of you to give me your day of birth. And as we are with about, well, I think we're with about 100 people in this bar, I thought that it would have a good chance that we have at least two people who share the same day of birth. If we take a look at this typical paradox, which is called the birthday paradox, if we look at a group of people, say we have 23 people, then the chances that we have at least two people sharing the same day and month of birth, then we have a chance of about, let me see, 49%. If we take 50 people, then the chances to have two people with the same birthday is about 97%, which is extremely high. And this is a typical paradox because the number of people is not very high. It's about 50, and still we have a very high probability that that two people have the same day of birth. It's not the year of birth, but it's the day and the month. So when I asked you to give me the day and the month you were born in, I had a pretty good idea that there would be at least two people who share the same day of birth. And actually it happened about halfway when I was through this bar. Then it happened that two people, it was November the 20th. There are two people here in this bar who share November 20th as their day of birth. So just as a token of appreciation, these two people will receive my book Statistical Tools. Okay. So that comes as a surprise. You know, with a small group, we have a fair chance that two people share their day of birth, and it's directly related to the formula I showed you today. Well, at the very beginning of this lecture, I told you that you know, one of the best things a teacher can do is change the worldview his students. And well, hopefully during this lecture maybe you change already your point of view. If not, maybe this is a more compelling case. This is about planet Earth and our universe itself. And here we have our planet Earth, and there are many people who ask themselves, how is it possible that such thing as planet Earth ever came into being, with all these beautiful oceans, with the animals, the forest, the rainforest, and all the vegetation that you can see here on this picture. And it's so full of life, and it the question arises, how could this ever been made possible? Well, in my opinion, I think that is the wrong question. My answer to this would be that there was no other way, because if we take this very important formula, and as I said before, this formula seems to me far more important than any other formula that is ever invented, because this formula tells you that if something has some probability to occur, and this probability might be very, very, very low, if we take a very long period indicated by t, then this very, very rare occurrence will actually occur. So if we take the universe, and if the scientists are correct, there is the universe came into being about 14 billion years ago, and our own Earth is about 4 billion years old. Now, if we assume that at the very beginning of our universe there was a very, very, very small probability that something like Earth came into existence, just based on all the elements that were already around, if we assume that there is some kind of probability, a very low probability, and if we take time and we calculate the probability, then at a certain moment the probability that there is not a planet Earth is very, very low. So if we put these 10 billion years into the equation, and we take a very, very low probability, a very low initial probability, and we put that in our formula, then it doesn't come as a surprise that after 10 billion years something like planet Earth actually came into being. It's just a matter of chance. So with this last conclusion, that if we got very, very rare events and we take a very, very long time, then this very rare event must occur. With this last conclusion, I would like to end this lecture, which is part of a longer series of presentations, all related to the week of chance, the Week van het Toeval, here at Radboud University. And if you have time, please attend the other lectures as well, because they're all very, very interesting, I believe. I'd like to thank you very much for your attention, for being here in this bar, and I wish you all the best, and enjoy the rest of this day. Bye-bye. Thank you very much. Nee.